Let's get started. Now that we are done with module 3 and exam 3, how was it? Fair? Nothing surprising, right? Okay. Okay, great. We are ready to start the last module, module 4, and this is about asphalt concrete. So we are shifting gear from concrete to asphalt concrete. And we'll start with asphalt binder, which is one of the ingredients of asphalt concrete. And that's what I'm going to do today. What packet that you have is actually 2 packets. So you need to bring this till the end of semester. There will be another packet which is for volumetric calculations, which I give it to you next. And these are the only packets, basically. We are approaching the end of the semester. Asphalt binder, if you haven't seen it, it looks like that. It's a sticky black liquid-like material. How many of you have seen asphalt binder? Right. Yeah, you probably have smelled it if you ever drive by where they have closed one lane and doing some construction. You smell asphalt. So we want to learn a little bit more about that. And as you see here, the main application of asphalt binder is in pavement construction, but not only. So just to give you an idea, we have 2 types of pavements. The pavement may be asphalt, concrete covered, and that is flexible pavement. So what you see here, it can be hot or warm mixed asphalt. So normally you hear HMA or WMA. This is abbreviation for hot mixed asphalt or warm mixed asphalt. And then we also can have rigid pavement, which is another name for concrete pavement. First, we want to see a little bit the difference between them and see why we use asphalt in pavement construction. Why not just concrete? So if you had a way to cut through a pavement section, it would look something like that. You have asphalt course, then you have base, sub-base, and subgrade, which is just another fancy name for soil, basically. And as you can see, the load of the wheel is distributed. First, the highest intensity is being supported by asphalt concrete layer, and then it becomes less when you come to base and sub-base, and then subgrade. Look at the quality. So as you go towards the surface, because you have more stress, you need to have higher quality material, which means that everything is more strict. Asphalt is a combination of aggregates, and so asphalt binder basically glues these aggregates together. But what carries the load are actually the aggregates. So you see these arrows, they show how the stress is being transmitted from the wheel down to the soil. So you go down like that. So what carries the stress is not really the asphalt binder or the aggregates, as you can see. And here we are looking at the asphalt pavement section again with a little bit of more detail. And you see that, for example, asphalt concrete layer may have 2 sub-layers itself, surface and binder course. And what I want you to pay attention here is what is in between them. So you see it says tack coat and prime coat. These are basically, these are also some, let's say, some, in emulsion, like you mix asphalt binder with water or with some solvent, and you spray it like glue so that the layers stick together. If you don't do that and you have several layers, then a truck may pass by and a piece of material may be sheared off. And this becomes very important in runways. Imagine when the plane takes off, and if there is, the asphalt may be really good material, but if it is not sticking to the layer below, it may come off when the plane is exerting shear on the pavement. And on the top, we also have another coat, why doesn't it write? Which is called seal coat, and that is to seal the surface, let's say for permeability, to make sure that you don't get too much water going inside the material. So that's how asphalt pavement section look like. Now let's compare this to rigid pavement. What do we see here differently? What is different here, just by looking at it? What is different? Doesn't right. What is different? Yes?
There's more concentrated load into the soil.
This is actually, the concentration is into concrete. I know the graph may be a little bit misleading, but this is the stress in concrete slab, and that's what the soil is taking. So what do we see here differently?
There's no base or something.
Exactly. The pavement, the slab is sitting directly on the on the subgrade, on the soil. So, and I know that the graphic looks a little bit misleading, but this is the stress that the slab is taking. And this is what the soil is taking. Actually, most of it is being taken by the slab. So in concrete pavement, we don't care much about what is underneath the pavement because the slab is doing most of the work. In asphalt, the other layers are also important, asphalt pavement. And this is how, if you want to compare them. There are other differences that, for example, asphalt pavements are much cheaper to start with. They may need more maintenance during their life, but they're cheaper. Concrete pavements are much more expensive. And that's why over 95% of the roads are actually flexible pavement covered. How many miles of roads do you think we have in the country? Total. Have a guess. It's about 4 million miles, over 4 million. So because of that, you want to have something which is inexpensive, and the material becomes very important, what you are using, because it's a huge investment. Okay, now that I hope you are convinced that asphalt concrete is a good material, used for many miles of roads, let's find out what it is. Typically, people just say asphalt, but asphalt is not asphalt pavement. They miss the ingredient, which is very important, and that's the aggregate. Right? If you just say asphalt, then you are just talking about the sticky black flowy material. So it's not what you see on the road. If you just use that, everyone would sink in, and there would be no pavement. So we want to learn to use the technical terms as engineers. So asphalt is kind of asphalt binder or asphalt cement, people say, and it's the glue for asphalt pavement, and also it's used for sealing or waterproofing. If you have worked in construction, or if you have been curious about the waterproofing of your basement, maybe you have seen that sometimes people use this black substance to waterproof, right? Has anyone noticed that or seen it? No? I mean, it's hard to see because you don't really see it, but if you ever have a problem with your basement, then you kind of have to see what is going on there. Anyway, Asphalt concrete is what people refer to as asphalt, and that's a combination of asphalt binder and aggregate, and also actually air voids. And that's the material you see on the road. And sometimes people call this AC. Right? And this is how it looks like. If you cut a portion and look at it, you see the aggregates, different sizes. Normally they are very angular. We will find out why soon. And then you have the sticky substance. And if you want to know how much of each, most of it is aggregate, actually. Asphalt is a small portion of it. What gives the material strength and stability is actually aggregates. So sometimes people also say asphalt, cement, concrete, but I haven't heard that very often. So normally you just hear AC. Okay, now we want to learn a little bit more about asphalt. So aggregates are very important. You can't just say asphalt pavement. And to kind of know why, it's useful to look at the relationship between the modulus of asphalt binder. So here we are looking at the modulus of asphalt binder with temperature. So what's the problem? If you don't use any aggregates, what happens when the temperature goes up? What do you see? What does this graph show? Modulus is like Young's modulus. It's going down. What does it mean then? If you make a pavement out of this material, what happens if the temperature goes up? The stiffness goes down. What is the consequence of that if you drive on this road? Well, your car sinks in. If there is no stiffness, so there is no support. So everything will sink in. So the point here is that asphalt by itself doesn't have any strength. It's really just the glue. And remember that asphalt binder is a viscoelastic material, and the properties are highly temperature dependent. It loses modulus. It becomes soft, just like caramel, when the temperatures go up. So you get into trouble if you use this material by itself. So what gives a strength and a stability is aggregates. Asphalt is not doing that. In fact, if you use too much asphalt or a wrong type of asphalt, you may have some problems with deformation, as we will see in a second. So this actually goes to 0. So stiffness at 60 degrees goes to 0. So, and we are talking about the surface of the pavement temperature. It's easy for that to go above 60 degrees. So then there is a big problem. Right. This is just to tell you that aggregates are very important and their properties. Okay. So we are going to learn a little bit more about asphalt first. And in the classification of bituminous materials, we have asphalt and tar. And then the products which matter to us in construction are this asphalt binder we talked about, and emulsion and cutback. And we want to learn a little bit more about each one of them. Bituminous materials, they are sticky, viscous. Remember, long time ago, you've learned about viscosity and viscoelastic materials. And also remember that you haven't taken any test on that. It wasn't included in exam number 1. So it is now a good time to review that material for 2 reasons. It's relevant to the discussion of asphalt concrete, and it will be in the comprehensive final exam. So it's a good time to look at it. If you look at the last homework, which I've posted yesterday or 2 days ago, you see that in the beginning I put together a review set of slides. So you can remember what viscosity was, how it changes with temperature, etc. That's when it matters to remember and download that information in your mind. So it's viscoelastic, sticky. It glues the aggregate together, and but it has also some other applications. We go back to that, and it's low cost, the one we are using, which is a good thing. So it's not like cement. Cement is more expensive. Tar is another bituminous material. This is similar in properties, but it's actually a product of distillation of coal. It's completely different, has a completely different origin. The one property which you want to know about and remember about tar is that it doesn't dissolve in gasoline. Why do we care about that? Because if you ever want to design, let's say, a truck stop or somewhere where you expect to see fuel spills, and if you use a typical asphalt binder, it can dissolve and your pavement can be, after a while, will get very much damaged. That would be one application of using tar. Otherwise, now people know that tar is not very healthy to use. It's hazardous. It can cause cancer. So their use in the US has basically, it's very restricted. Otherwise, it has very similar properties. It's being used sometimes for waterproofing, where you don't have any, you don't touch it, or it's not like exposed to people. It doesn't create any kind of hazards. Questions so far? Yeah, this is more descriptive. It turns out that we can get asphalt from nature. Has anyone seen like an asphalt lake somewhere by any chance? There are, not very many anymore, but there are asphalt lakes. For example, this is in Los Angeles, I believe. There are also rocks which have asphalt in them. This is, I think, in Alberta, in Canada. So you can have them in nature. But the one that we use for pavement, it doesn't come from those sources. It's typically the byproduct of the distillation process in oil refineries. So you take all the good stuff out, and what is left, the residual, is asphalt at the bottom. So it's a byproduct, and you use it as it is, right, as asphalt binder. If you mix it up with water, you get emulsions. If you mix it up with other chemical solvents, you get what we call cutback. These are the three most important products, bituminous products that we use in construction. So it's a byproduct of oil refineries. And that's why it is relatively cheap. And these are these products, asphalt cement. I told you this is being used for construction of hot mix asphalt or warm mix asphalt. You have emulsion, which is used mostly for maintenance. Cold mix, I explain to you what it is in a second. Cutback, the same as emulsion. And we don't use it that much anymore because this is also turns out to be hazardous for health. Now that we know more about the adverse effect, we don't use it as much. So these are kind of the main three products that we use. And we want to talk about each one of them a little bit. Asphalt cement we talked about quite a bit. We need to learn what emulsion is, what cutback is, before going to asphalt performance grading. So remember that the emulsion, for example, is being used mostly for maintenance, but asphalt cement is more versatile. And I think I mentioned that HMA is hot mix asphalt, and WMA is warm. Patching is obvious whenever you drive somewhere and you see like patches of kind of a different color of asphalt, that's patching. Overlay is when you place a 2-inch, about 2-inch, or 1.5-inch layer on top of an existing pavement. This is being done, for example, if the traffic volume has increased, your pavement is not sufficient anymore, or if you have so many deteriorations that if you want to patch, the whole thing would be patched. So you just decide not to patch and just put a new layer over the pavement. You have seen this happening, I think if you pay attention during the construction jobs, you have seen this, that the construction crew is doing that. It's fast and easy and people do that. Okay, hot mix asphalt, you have to heat up the ingredients and mix them and place them. We talk about placement and construction of hot mix asphalt at the very end, so we keep it brief right now. Emulsion is when you heat up asphalt a little bit and you mix it with water. So that's important. This is water. And what it is what you see here. You have small particles of asphalt. They are kind of dancing around in water. And for them not to make clusters and clutter together, you add emulsifier. So emulsifiers are similar to water reducers. They have charges, so they attach themselves to asphalt particles, and they make the particles all to have the same charge. And particles of the same charge, they repel, and then they go away from each other, so they don't make like clusters together. And that's what it is. How it is being used? Well, you basically mix it with aggregate. Now, you have to be careful to mix it with the right aggregate and use the right emulsifier. That's the important thing here. For example, limestone aggregates have positive surface charge. Igneous rocks have negative surface charge. Now, for example, here, this aggregate here has negative surface charge. For this to work well, you need to use an emulsifier which makes the particles of asphalt all positive. So that makes the asphalt stick to the aggregate. If you use negative and negative, it's going to be rip off. Does it make sense? It's simple. So you mix it and you wait 1 or 2 hours, the water evaporates, and then the aggregates stick together. This is called cold mix. So you don't use a very high temperature or anything like that. And you use it typically not to pave an entire section, you use it for repair. If you have some sort of small job to do, you want to do it fast because you have a high traffic section, etc. This is what you could use. Any questions about how it works? Charges? Great. Cutback, exactly the same way. The only difference is it's asphalt dissolved not in water, but in some chemicals. And because of that, we don't use it as often anymore, because these chemicals, when they evaporate, if you breathe them in, you may get sick. So it is hazardous. And also chemicals are typically more expensive than water. So we kind of don't like this very much anymore, but you may hear this name, and it was used before, so it's important to know what it is. In terms of the mechanism, just like emulsion. Great. Any questions about that? Everyone written down everything? Okay. Now that we made this introduction, we know what asphalt is, what are the different applications, etc. Now we need to learn a little bit about what type of asphalt to use where. And this is when I have to kind of download some of the information you have from viscoelasticity. I know it's been a while, but this is what we have to do. So asphalt binder is a viscoelastic material. What does that mean? You've heard this term before. Viscoelastic means it's both viscous and elastic. So it's partially elastic, partially viscous. What was the main difference between a viscous material and an elastic material? Yes. Exactly. So it has something to do with reaction. Elastic materials, they react immediately. Remember when we were drawing these strain versus time diagrams? The moment you apply the stress, you see the deformation. And as your friend said, if you remove the load, they recover immediately. Viscous materials, the properties are time dependent. Another important thing was that everything is temperature dependent. Do you remember this curve where the viscosity and temperature, what did we learn? If temperature goes up, what happens to viscosity? Up or down? Oops, yeah. Viscosity goes up with temperature? It goes down, right? What is viscosity? It's resistance to flow, right? Viscosity is resistance. So if you heat up the material, then the molecules, they can move more freely, and the viscosity is going to go down, right? Now you need to remember this to be able to follow and answer questions for this module. So if you have forgotten, please check first those review slides in the beginning of homework number 9 or 8, I believe, the last one I have uploaded. And you can also, of course, review the notes from the beginning. So the temperature becomes a very important factor here, because viscosity versus temperature looks like that, right? I even showed you how the caramel with temperature looks like, I remember. Something which is maybe less clear, because we only talked about quasi-static loading, is loading rate. So if the load is very, very fast, if it is being applied at a very high rate, for example, if the truck is going with a very high speed, this kind of works like low temperature. It goes to the dynamic loading, so just know that if the highest speed, it is almost like low temperature in terms of how it affects the behavior of the material. High speed means that high loading rate. But since this is mostly, we use this for pavement, it translates to a truck which is driving very fast. And vice versa, of course. If you have low, this behaves like high temperature. Okay. So now with this in mind, let's look at some of the properties of asphalt which are very much related to temperature. This is just to show you, I don't know why this slide is a little bit out of place, just to show you these different applications. What I showed you, like hot mix asphalt, if you have never seen it, this is how it looks like. Fog seal is a diluted asphalt emulsion. So you just spray it, let's say, for sealing purposes, as you can see here. And chip seal is some word for a cold mix. So you kind of can see that we have aggregates here, and then you go over with adding asphalt emulsion, and then you let the water evaporate, and then you have a nice layer sticking there. Now kind of we need to understand what type of asphalt binder we need to select for what application. And to do that, we want to see if we mess up, what type of problems we get first. So we go kind of reverse engineering in a way. Now these are the common types of deterioration. I encourage you next time you drive, don't be distracted, but try to look for some of these problems. So we see here a crack which is transverse to the road. Have you noticed ever something like that? Not so, and this is very extreme, but a little bit like on the road, it would look like that at the wheel path, the asphalt is a little bit, there is like a valley and a hill, something like that. You should have noticed. And this kind of network type cracks. These are the three problems. And you need to know these three types of problems. So we have low temperature or thermal cracking. We have the second one, so this is the first one. The second one is rotting. And the third one is fatigue cracking. And we want to understand each one of them a little bit better because, as I said, the purpose is to choose the material such that none of this happens. That's kind of the purpose. So sometimes this is also called low temperature cracking. Oh, it's written here. Rotting is rotting and fatigue cracking is fatigue cracking. Okay? Now, just to make sure you remember these three terms, try to write down which one is in this figure. I will show you. This one is, let me see actually, I didn't check. That's it. So, yeah, I guess it's simple. So rotting happens, for example, in high temperature when the asphalt binder, what happens to asphalt binder in high temperature? The viscosity goes down. That means it flows. So under the load of the truck, the material, because the glue between the material becomes very soft. So the material is going to be pushed under the wheel of the truck, and then you are going to see this kind of hill and valley kind of shape. Of course, it doesn't look hopefully like that. This is very extreme. But if you pay attention, you see this, especially if you travel to places where the temperatures can go high in summer, if they don't do a good job. Fatigue cracking, it's really because of repetitive loading. We have learned about fatigue before, right? It starts from the bottom, and then it comes and makes this kind of network cracking under the wheel path, typically. That's how you find out this is happening. So it happens under the wheel. And thermal cracking is transverse to the road. So this is the lane. This is transverse. During the cold season, if the material doesn't have a very high viscosity, it's brittle, it wants to shrink, it doesn't have the and then it basically cracks. That's what happens. And typically, you see that it's periodic, like it happens every, I don't know, 10 meter, 30 feet. And you see that it's kind of like that. So the purpose of studying these is to be able to design the right material. So now, what happens? What type of material we have to use? If we use low viscosity asphalt binder, what do we expect? Do things improve or get worse? If we use low viscosity material, do you think low temperature cracking becomes worse or better? Do we have less or more thermal cracking? Less, right? So if you expect something like that, if you expect really harsh winters, you actually want to use an asphalt binder which has low viscosity, which means that it flows easier. So it is not that brittle in low temperatures, right? Remember, when you increase the temperature, viscosity decreases, right? So the temperature, if it is very low, you have high viscosity. High viscosity means that it becomes more like a solid. And if it is more like solid, it doesn't deform easily, you have more cracking. So low viscosity asphalt is better. It's a better option for cold regions. And again, remember how it looks like. This is, I think, a good figure. So it really transfers to the lane. How about rotting? How can we choose a good material to minimize rotting? Low viscosity or high viscosity? High. And you want to make sure that this material doesn't lose viscosity with temperature a lot. So it should be high viscosity, and the viscosity should not change. I call decrease is better than change with temperature increase. That would be the best material for a very warm region where you expect to have very hot summers. Okay. Yeah, you see here, for example, I mean, this is more like you see where you have deformation in the material. So, how about fatigue? I hope that you still remember that we had something called SN curve, where you see the strengths changing with the number of load repetition. And one of the examples that we saw, if you remember, was the number of cars on a highway long time ago. Right? So we have this kind of behavior. And fatigue cracking is caused really by repeated loading. This is a good picture. You see where the wheel path is here, and you see that network of cracks. That's because of you are basically exceeding the maximum repetition of load that is allowed. Now, what type of material would you choose if you suspect that, for example, you are working in an urban area that you think maybe the traffic would increase a lot during the time, the service life of the pavement? Low viscosity or high viscosity? Lower, right? You would prefer also here lower viscosity material. Again, if the viscosity is higher, the material flows less. It's more brittle, more susceptible to any kind of cracking. It doesn't deform as much, right? Great. So, if you have a project, do you think what is the main parameter that you have to consider if you want to decide on your asphalt binder. Temperature. You have to look at the, now this is extreme case. I don't know, with this weather in April, I guess it's also kind of, when you look at that picture on the right, it feels nostalgic, like, okay. It's extreme cases, but the number one factor that you have to look at is the history of temperature, seasonal variations in that location. So, temperature. And you'll see that temperature has a big say in deciding and what materials to use. Okay. And it's not only just the temperature, it's also important to look at the material, of course. The viscosity becomes very important. So this is the so-called viscosity susceptibility curve. And let's see what it is. It's a little bit sometimes difficult to understand what this is. This is here on the y-axis is viscosity, and here is temperature. But pay attention, this is logarithmic scale. So what you see is how the viscosity is changing with temperature. It decreases, but it is logarithmic. So if it is, of course, very high, the material is too brittle. If it is very low, it's very hard. This we know. Now, if you have several of these, they are parallel to each other, but the susceptibility is very different. Here, the temperature could be, let's say, from 1 to 10 degrees. Then it is, let's say, from 10 to 100, 100 to 1,000, because this is logarithmic. As we go to the right, the viscosity is actually not changing much with a lot of temperature change. So these are parallel, but they are very different from each other. So that's one thing I want you to pay attention to. Is this clear what I'm saying here? If it was linear, they would all be the same. But since this is logarithmic, that means that this on the left, on the right, this on the right-hand side, that means that for a very large temperature change, the viscosity is changing as much as this one on the left-hand side for a small temperature change, because this scale is logarithmic. So this can be just 1 to 10 degrees here, and this could be thousands of degrees. Does it make sense? Okay. So that's another important thing. So this is kind of called soft graded. This is hard graded. So other than having a high or low viscosity, you also have to see how the viscosity is changing with temperature. Because you can start with a good material, but if it loses viscosity at temperature like that, it's not going to be as good for a certain application. So soft graded is better than for cold climates. You want to use hard graded here for warm climates, because you don't want the material to lose viscosity at high temperature very much. Otherwise, you're going to have a lot of running before. Is this clear what I'm saying? This logarithmic scale here is kind of the tricky part to pay attention, right? Great. Any questions about this? It turns out that you should also be worried about what happens with asphalt over time. So the asphalt ages. When it ages, the viscosity goes up. It turns out that if you just build pavement, the material is not going to be the same if you look at it 20 years afterwards. And what happens then? if the viscosity goes up, it becomes more brittle, right? And then it becomes more susceptible to low temperature cracking and fatigue cracking. So everything goes back to viscosity and how it affects the deterioration of the material. So this has to be taken into account, and there are tests which test the aging of asphalt. So when we talk about aging, this is what it is. It's not about just the age, like if it is older, like the guy you see here. And if we want to make it more formal, this is how it looks like. So we can think about 3 phases. In the beginning, you will start with certain viscosity. During construction, the viscosity, like this is the short-term changes, but it's dramatic. Why is it that way? Because during construction, the material is typically exposed to very high temperatures, and also it's exposed to a lot of air. So you mix things, you really you play with the material a lot. So during construction, you change the material property a lot. So it turns out that then that affects the viscosity, but then afterwards you have kind of a slow increase. It increases, but slowly. And this is the long term. And there are tests that we will see that assess how much aging you will have for a certain type of material. I guess this is where I stopped in the morning. That's where we stop here. We start with performance grading.